Hi students, in this video we're going to talk about infinite limits. So our main idea is that infinite limits they occur when a value increases without bound, which means we're going to go to positive infinity, or the values close to value point decrease without bound, which means that the values are going to go to negative infinity. So we're going to open up Desmos so we can draw the graph of this function f of x equals 1 divided by x squared. So let me see. Desmos is here. All right, so I already have the graph drawn, and I have this table that we need to fill out, completely filled out. So, and we're going to examine the limit when x approaches 0. So now we can see when x gets very close to 0 that our y values get incredibly large very quickly. So we can look at the function and see for 1 over x squared that x clearly cannot be 0, which means that we have an asymptote at x equals 0. So let's get the basic shape of this graph. We know the point 1, 1 should be on the graph. And the rest kind of doesn't matter. We just need to get it close enough. We know the point 1/2, 4 will also be there. So our graph looks something like this. And it's symmetric around the y-axis, so we're going to get the same thing on the right side. So our graph looks something like this. And if we're filling out the table, when we had -1, we had 1, and then I believe, what was it then? 100, 10,000, 1 million. So we had 100, 10,000, 1 million. And this was undefined. And then we're going to repeat the table. So then we had 1 million here. And we had 10,000. We had 100, and we had 1. So we can see that when our x's get close to 0 in either direction, they grow without bound. That's going to mean that the limit when we approach 0 in general is infinity. So if we have to describe what happens close to 0 using limits, we would say something like the limit as x approaches 0 from the left for our function. And based on our table, we see that that limit is positive infinity. And we can also say that the limit as x approaches 0 from the right for f of x is infinity. So remember, when we define limits, we said the limit existed when the left limit and the right limit are the same value. So in general, we would say the limit as x approaches 0 for f of x is equal to positive infinity. And so when we have asymptotic values, our limit is always going to be negative infinity, infinity, or if the graph branches in two different directions, the limit will not exist. So the key to understanding infinite limits is we just have to consider the ratio of the numerator to the denominator. Since we actually won't ever be able to substitute in the asymptotic value, we choose values very close to it and just look at the sign to see which infinity the graph will tend towards. So in this first example, we want to find the limit as x approaches 4 from the left. Now we clearly see that we have x equals 4 is a vertical asymptote. So since x can't actually be 4, we'll say choose x equals 3.9, a value slightly less than 4. And so if we do that, we get, so 3.9 plus 9 divided by 3.9 minus 4. Now, all we care about is the sign of the number. We don't actually care about the number because the limit is always going to be infinity, negative infinity. So we know that 3.9 plus 9 is positive, and 3.9 minus 4 is negative. So in this direction, we know the limit is going to be negative infinity. For the limit when we approach 4 from the right, we can choose, we'll say choose x equals 4.1. And some of this you can do mentally once you get the hang of it. So we'll say this is roughly 4.9, 4.1 plus 9 divided by 4.1 minus 4. In this case, we're going to get a positive value divided by a positive value. So this is going to indicate that this limit is going to go to positive infinity. We'll actually put the positive. So the limit as x approaches 4 in general, we would say does not exist. And the reason is because the limit as we approach 4 from the left for x plus 9 divided by x minus 4 is not equal to the limit as we approach 4 from the right for x plus 9 divided by x minus 4. And that's all we do. So for our next example, it might be our last one. We have the function x 3 minus x divided by x squared minus 4, and we want to find the limit when x approaches 2. So let's see. If we find the limit when x approaches 2 from the left, for 3 minus x over x squared minus 4, say we choose x equals 1.9, for instance. So we would get 3 minus 1.9 divided by 1.9 squared minus 4. So that's going to equal a positive value. And whatever 1.9 squared is, 3.61, by the way, 3.61 minus 4, that's going to be a negative. So this is going to indicate this limit is negative infinity. Now, if we did some value slightly greater than 2 for this function, so 3 minus x divided by x squared minus 4, and we choose, I don't know, x equals 2.1, then we're going to get 3 minus 2.1 divided by, divided by 2.1 squared minus 4. So that's going to be a positive divided by a positive. So this limit is going to be infinity. So in general, this limit does not exist because the left limit and the right limit aren't the same value. Next, we have this function x cubed plus 5x squared minus 24x divided by x squared minus 9. So I would factor this so we can get some sense of what's happening. So we're going to factor this to get the limit as x approaches -3. And we can factor in x out of the numerator because it is the greatest common factor. So that's going to give us x times x squared plus 5x minus 24. And in the denominator, we would get x plus 3 times x minus 3. We can factor the x squared plus 5x minus 24 to actually be x plus 8 divided by, x plus 8 times x minus 3. And so we'll take this out. And what that allows us to do is cancel the x minus 3's. So we get the limit as x approaches -3 of just x times x plus, that's x plus 8, divided by x plus 3. So we clearly see that we have a vertical asymptote at -3. So our limit is going to be negative infinity, 0, or infinity. So we can just do some inspection. So we'll say something like if x, or actually let's set this up like we've done the previous problems. So we just need the left limit and the right limit. So the limit as x approaches -3 from the left, And you know what? Let's call this f of x. We'll call this h of x, so we don't have to keep writing the entire function. So if we are using a value slightly less than 3, slightly less than -3, that's going to give us a negative value times we'll say negative 3.1. So negative 3.1 plus 8 is a positive value, and then negative 3.1 plus 3 is a negative value. So that is going to give us a negative times a positive, which is a negative value divided by a negative, is going to indicate positive infinity. So again, imagine we had, we can actually write the number. So we'll have negative 3.1. We're multiplying that by negative 3.1 plus 8 and dividing by negative 3.1 plus 3. So that's our negative, this is our positive, and this is our negative. Again, we don't care about the actual number, we just want the sign of the number. And so a negative times a positive divided by a negative value is going to give us a positive. So we end up at positive infinity. Now, if we do the same thing for a value slightly greater than -3, then we're going to get, say we use negative 2.9. So we're going to have a negative 2.9, which is going to be a negative, obviously, times negative 2.9 plus 8, which that's still a positive value. So that's a positive value, and divided by negative 2.9 plus 3, which is also positive. So a negative times a positive divided by a positive is going to give us a negative infinity. So this limit, it does not exist, again, because the left limit and the right limit are not the same thing. For our last example, we have tangent x. So we should already know that tangent has asymptotes at all of the odd multiples of pi over 2. So let's rewrite tangent to be sine divided by cosine. So we have the limit as x approaches pi over 2 of sine x divided by cosine x. So let's actually look at this graph in Desmos, because choosing values slightly less than pi over 2 is a little bit trickier. So we're going to put in our function, we have tangent, we have x. So, and we'll do x equals pi divided by 2. So you can see here is where our asymptote is. And if we want it to look like asymptote, let's make it behave like one. All right, so now we have an asymptote. When we approach pi over 2 from the left, our limit is infinity. But when we approach pi over 2 from the right, our limit is negative infinity. So here, this limit does not exist for the same reason. The left limit doesn't equal the right limit. So again, the only time the limit is going to exist is like in the case of our first example, where we had infinities for all three. But all we have to ever do is check a value close to the limit, the asymptote, and record the sign, and that's going to be our infinity. All right, that concludes this video. I'll see you all for limits at infinity next.